So we were playing around. And my goal here was to start off, how do you get a circle of any kind? Right? Then, well, how do you make the circle go the other way? Right? How do you do it once, then stop? So what we're doing is we're adjusting various parts of the vector value function. There's the limits on t. There's the function itself. You remember also the speed at which you do it. When you work with technology, that made that one that looked like a hexagon almost, right? That wasn't a circle, right? And we had to graph it with a smaller delta t. Right? Okay. Here's another one. Our circle presently starts and stops right here. Whether we went this way or this way, right? How would I make it right here? How would you trace the circle in the opposite direction, beginning at the top? So you want to begin at pi over 2. And you want to go this way, clockwise. So that was the opposite direction. The initial direction was counterclockwise. Now, it will help if you apply some basic transformations of functions. What do I mean? That how do you shift up, down, left, and right? How do you shift the function? Well, you shift it horizontally. Like if I want to take the graph of something and I want to shift it horizontally, I substitute. If I want to shift it to the right, say 5 units, I substitute x minus 5 for x. X minus 5 puts me in the shifts in the positive direction. X plus 5 would shift in the negative direction. So now, what am I doing? I want to start at a different place. I want to start up here. Now, t was, depending how I did it, if I put the 2 pi in, let's say before I put the 2 pi in, t was my number of radians. And so when t equals 0, I want it to be up at pi over 2. Top of the circle is pi over 2. Everyone with me? So when t equals 0, I want it to start at pi over 2. So that's a concept, right? So let's go to our calculator. And I'm going to get rid of that. Get rid of the 2 pi a second. Now we said this traces. Okay. This should trace how? Which direction? Clockwise or counterclockwise? Should this trace? The way I've corrected it. This is pretty much my original. It should trace. You're looking at it should start at 0 and trace that way, which is counterclockwise from your original. Right. So let's see if we're right. Oh, we got to go and let's do. Good. All right. Good. So let's trace. See what we did. Good. You see how slow it's going? I should have. Oh. We got to readjust our t here. We only have t going from 0 to 1, right? And so I need it to go to 2 times pi. And then let's step that up to 0.1. a little faster, right? Trace. Okay. That worked. The good news is that, like we discussed, the bad news is it's wrong for our particular problem. So we're going to start with that and make adjustments. So to make it what do you want to do first? You want to make it start here, or you want to make it go the opposite direction? Well, we discussed before. To make it go to the opposite direction, we put minus t in for t. Also, we saw that cosine of minus t equaled cosine of t. So we didn't have to make any adjustments to cosine. So if we put minus t for t in here, it would be the same. Because cosine is an even function. The cosine of negative pi over 4 is the same as cosine of pi over 4. It's the x-coordinate. But we do need to put a negative in there. Right? So I'm doing all this for review. Right? And I shouldn't be doing this from the keyboard. But so this should go opposite direction. Okay. So we're adding that back. Now I want to start at the top. So just think. Let's do the scroll on top here. Just think. If it's going to start at the top, at t equals 0, I need that value to equal pi over 2. There's two ways to do this. Well, two ideas come to mind, I should say. Idea number one. Up here, I could just add pi over 2. If I put t plus pi over 2 and minus t plus pi over 2, if t is 0, they would both be at pi over 2. Let's see what happens. So I go here, hit insert. Then I need to add plus pi plus. Now, do you see the motivation for this? Is that, well, if t equals 0, those two will be 0, and I got pi over 2. So whatever this does, it's going to start at pi over 2. Okay, right? Ready? Trace. See what happens. You see what direction it went? Right, it went like this. It went like this. That's the wrong direction. Yeah. Okay. All right. Let's go over here. How did adding pi over 2 change direction? Think about that. Let's think about it. I'm not going to tell you. I'm not going to tell you. Let's go back over here. Let's do this one. So we have 2 cosine t. Down here we have 2 sine minus t. This is what we had, and then we added the pi over 2, right? We expect this to go the opposite direction. We expect this to go clockwise. Here we go, you ready? That one went clockwise. How did adding the pi over 2 make it go counterclockwise? Let me tell you what the problem was. Rather than trying to figure that out, this is a really common mistake. The reason why is I've made it a million times. Okay. I see students make it all the time. You remember your transformations functions. You had shifts. To shift the graph up or down, you just added like the number or subtracted the number. But to shift it left and right, it's counterintuitive, number one. So to shift to the positive direction, you had to do minus. So you had to go x minus 3 or something to move it in the positive direction. Right? And x plus 3 to move it in the negative direction. So it's counter. Secondly, it was a substitution. What is that? So everywhere in a function, if you want to shift it to the right, 3 units, you substitute x with x minus 3. You don't just add 3 to x everywhere. It's a substitution. Or subtract 3 to x. Because that's not going to work. That's not going to work, trust me. What did we do here? We just added pi over 2 there. Right? That's not how you do it. What we have to do is we have to do a substitution of x to x, either plus pi over 2 or x minus pi over 2. So here. These are my original functions here. When I say x, I mean t here. Right? So I go up here. I got the plus pi over 2. Down here, I just added pi over 2. This isn't a substitution. Neither one of them really were in our concept. But so down here, if I really substituted t plus pi over 2, the negative sign would apply also to the pi over 2. Don't you see the difference here? So we're going to go. It's not going to make a difference on the cosine because there's no negative there. Second insert left parenthesis. Let me go down here. I'm going to put a double right parenthesis here just for emphasis. You see how you're taking the negative t plus pi over 2? So this case, you've substituted t plus pi over 2 in for t in both of these instances. But in so doing, the negative applies also to the pi over 2. It also has the desirable feature that when t equals 0, oh, look what we have. Here. Let's see what happens. That's awesome. Before it started. See where it started? The t plus pi over 2 started down here and not up there. How did you fix it? See, this is my attempt at making the calculator a learning tool. Because you know how long it would take to actually plot points or put these on a sheet of paper? Right? It started down there. Why did it start down there? Oh, dear. I needed to start up top. How about if we do this? That went in the right direction. What's the point? The point is these are involved. These are really, 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 really applied. Really applied, right? This kind of thing is done in industry almost every minute in the industry. My son brought home a problem that they were dealing with in his job. Okay, right. They had a. This is exactly the kind of stuff. They had an arm that goes from say here to here, and it's an arm of fixed length. So the arm is maybe 2 feet. So the arm has one part here along that edge, and the other part is a fixed length, say, just for the sake of argument, 2 feet. And then here, there's a tool that does something to a circuit board. You don't care. It doesn't matter what it is. But they need to be able to draw straight lines with that tool. Okay? And the only things they can adjust, is the angle, this angle right here, theta. Theta? Okay? And they can adjust this point here, this way and this way. How do you draw a straight line that's at an angle? What's the relationship between theta and the position here on this axis? This is a vector value function. And similar to what we're doing now, right? And my son brought this home one time. That was actually summer for camp. He brought it home. He came home a few days earlier and worked on it on my kitchen table, right? The industry's doing this all the time for different things and motions, right? So it's here we go. That was actually what was already here. I put the answer in this. So the it is a brain twister because you got angles here, which we're not real super familiar with working with, right? And then you got the direction, which counterclockwise or clockwise, and then the starting point. All that played in to answer these different questions. So it got more sophisticated each time. Sketch this. This is almost going to seem easy compared to the other. Right. First of all, I have a Z there. We have a K here. We didn't have a K in the last one. If it was just this, what would it be? Circle. Be what we've been doing the last probably entire period, right? Last time we used it. This is going to do what? This is going to make it go up and down, right? So if it didn't have that K component, you would have if it didn't have the K component, don't write this in your paper. It would start with a positive x-axis, and it would go. It would just trace a circle in the xy plane, right? Starting right here. But it has a K component. So what is that going to do? Well, the K component is going to be T. So as T goes, it rises. It rises at a constant rate. However fast T's going, it rises. So at T equal 1, it's 1 unit up. T equal 2 is 2 units up. T equal 3 is 3 units up. Okay? So let's get rid of that. What's that going to make that circle do? It's going to turn it into a coil, a spring. So it's going to go like right? Now, imagine that point. It's going to have the same radius. From the top, it's going to look like a circle, right? When it goes one lap around, that is going to correspond to 2 pi on the z-axis. So when t equals 2 pi, it will have made 1 coil around. All right, and then up here again, that's 4 pi. And so on. Okay. And the distance between these coils, between any 2 coils, is going to be 2 pi. And it's going to go down. That. So the new things in this problem are what? We have this z. You're not just doing x, y. But if you were to, an observer, if you were around this thing doing its thing, if you looked at it down the z-axis from the top, if you look at it down the z-axis from the top, it would be what? It would be a circle. If you looked at it from the side, it would almost be a zigzag. And we should put little arrows on that to be. Just going to keep going. Right? What about this guy? Here's a little up. And actually, we're going to change this in your notes to. I don't have nearly enough homework in these slides. So this is section 12.1, the first homework problem. I want to add more homework in the slides. Even students have asked me to do that. You guys know that. You're probably going to get an 8. Okay. Cycle. This is where this kind of goes. This is going to be the problem you love to hate. But it's going to learn you something. Imagine, let me see here. Imagine a, word's out of alignment again. Imagine a circle. Like that. Picture a plate or something. Something fixed and round. And then you have a point at the bottom of the plate that's sitting on the origin. And you're going to roll the plate. You're going to roll it on the x-axis. Right? It turns out that the point will trace out a curve. Looks like this. And as you might suspect, it does this. It keeps going like that. And over here you have the circle finally here at the end, right? And here's a center, right? It's going to make like an arc. That arc is called a cycle. It has some special properties that are used in, again, in mechanics. What are mechanics? It's basically the physics of moving things, usually constructed things. Very hard class in college. Mechanics and statics too. Mechanics is usually moving stuff. Statics is the forces on a fixed object, a rigid object, like a bridge, something. You have all these different joints, right? And you're interested in what are the stresses on one particular bolt or section of bridge or something like that. That stuff is extremely, extremely important. Extremely important. So, question. What's the equation of that arc? Hello. What's the equation of that arc? So it's good, it would bounce like this, right? One. Keep making up, right? Write a vector valued function that traces one arch of the cycloid of radius 1. One arch. And I'm going to end class today with a I'll teach you. You may not know this. Some people don't know this. All circles have the same radius. Yeah, I want to prove it to you. Last couple minutes. It looks like this. So I want one arc. Well, this is the way to break this down is twofold. One, ask yourself, how do I make the circle rotate in the right direction? And that's what we've been doing the last several slides. The second is, how would I make the circle rotate like this? Radius 1, right? So this is the point right here. 0, 1, right? How would I make that circle rotate starting at the bottom, not starting that way, of radius 1, but 1 unit up? Everything we've been doing, the center has been at the origin. How about if I don't want it at the origin, I want 1 unit up? Then, how do I make it move? How do I make it move? How do I make that center move this way? Okay. All right. So we have a couple different principles we're going to introduce here. Number one is we're going to break this down into 2 vector value functions. One is going to track the point with respect to the center. Point with respect to the center. That's what we've been doing, really. Making it go a certain way around the center. Right? We haven't been making the center do anything. So one vector value function is going to track the point with respect to the center. The other one is going to track the center with respect to the origin. And what does the center do here? As this wheel, as the wheel turns, that means nothing to this generation. Every single person my age growing up, if you would say, even 40 or above, as the world turns, everybody would know what you're talking about. Does anybody know that phrase? As the world turns, it was even made. It was a soap opera. They don't mean that soap operas. There were these daytime TV shows that every single day had an ongoing story. They had an ongoing story, and the story never ended. Some of them went 20 and 30 years, the same daytime thing. People went in and out, got divorced, married, grew up, had grandkids. Some of the same actors were on these shows for years. Unfortunately, they got more and more sleazy. They got to be almost like running romance novels. Okay. And they faded, and stuff like daytime talk shows like Oprah and stuff came in. And that's what's on channels now. But as the world turns as well, days of our lives as well. So as this turns, this thing is going to move from here to here. The center. So we're going to track, we have 2 things. The point on the circle with respect to the center, and then the center with respect to the origin. Okay. Phrased a different way, it would be this. We're going to track the point like this. Just let's take this center right here of the second circle. We're going to track this one. That's the point with respect to the origin. And then I'm going to track the center with respect to the origin. Then I'm going to track the point with respect to the center. So I need two vector valued functions. I'm going to call these R, let's see here. I'm going to call this one R1 and this one R2. Okay. So R1 tracks the center with respect to the point with respect to the center. So R1 is going to equal 1. And we're not going to have time. R1, very similar to what we've already done. It's going to be cosine of something I plus sine of something j. Now, I'll give you a hint. We've already done a lot of work on this. We did a problem, did we not, where we had we need this to start with a point down at minus pi over 2. We did one with it at pi over 2. In fact, one of our mistakes was making it start at minus pi over 2. Correct? Anybody remember what that mistake was? If you go back a few slides. Down here. We had the plus right there. I need to start down. So let's go back. Calculator. We no longer want it to be radius 2. And by the way, that minus can come straight out, right? It's not a big deal. So up here, plus there, plus there. Now, we already did the thinking behind that. I'm not going to do it again, but this should, when I hit trace, that should start at the bottom, be a smaller radius, start at the bottom, and go this way. Clockwise, right? Ready? Right. So that's going to be cosine. That was a t plus pi over 2, right? Right? And then we had a minus. We'll bring the minus out. T plus pi over 2. We already did the work behind that. That was the lead up of all that, right? All that was lead up to this. The other thing is, how would I make a point go straight across? Well, what's the coordinates of this point right here? It's going to have a y coordinate of 1, right? The x coordinate is the circumference of the circle, 2 pi. So R2 is just going to be Ti plus 1j. Now we only want one arc. So I'm saying that will just go straight across. That will be this blue line right here. We want it to stop though. We want it to start at the origin and stop at 2 pi. So we're going to do 0 less than or equal to t less than or equal to 2 pi. And our r, our final ones, these two added together. So if I add that and that together, what do I get? My r of t. What do I do if I add the x coordinates? I'm going to have t plus cosine t plus pi over 2 I. And then I'm going to have plus 1 minus, that minus sign right there, sine t plus pi over 2 j. Right? Turns out that simplifies some, but this is our correct answer. All right, and we'll play with that more on that. I didn't have time to give you my paragraphs. Go to that next one. I might even have to bring a prop. I got to talk to my wife into bringing a dish from home. What's that? Yeah, I know. Yeah, for good reason. For good, you know what? You know what? Yeah, that's a good idea. You see that? There you go. I wrote a bulletin article in East Hills Bulletin for Mother's Day called, you've heard necessity is the mother of invention. I wrote one called Mothers of the Necessity of Invention. If you want creative answers to something, put some moms on the project. Okay? Put some moms on the project. They have had to improvise everything. Put some moms on it, you're going to have solutions you didn't think. Thank you.
At 4.
Oh, okay, at 4, yeah. And I'll see you 3 or 4. Okay, good. You're already done, dude. Yes. Have fun this week and playing baseball.